All right, well, thank you very much. I'll be giving you a brief introduction to GPUs, and this talk targets some varied levels of knowledge, and so feel free to interrupt me at any time if I'm being too basic or too detailed if you want clarification. So I'll start by showing some screenshots. These are what GPUs were built to do, and these are what GPUs do on my computers at home. They run video games. And hopefully you can see enough detail in these images here that the detail over the years from 2003 to 2011 here, I've shown screenshots from a series of games. The detail is increasing exponentially that they're putting in these games. And screens today have millions of pixels, and say back of the envelope, tens of thousands of calculations are put into the coloration and the shading and the shadows into each pixel. And these are interactive games. They respond to your user inputs in real time. So you have 100 frames per second. If you multiply all those numbers together, you get a teraflop. So that's the kind of level of performance that video games demand today. On the flip side, there's a relatively new market for GPUs. And I'll get to general purpose computing in a moment, but right now, this is what makes cash for the GPU manufacturers. They produce GPUs to do video games, and the science is a side effect and kind of funded by what they do here. But going forward, there are a lot more cell phones out there than there are video games. So as they put more and more GPUs into these types of devices, these will become the cash cow for the industry. And so us on the science side will have to think about, well, how are we going to leverage this for science? And I don't know the answer to that question right now. But these devices demand, whereas the video games demand extremely high performance, these devices demand low power so that you get a battery life out of them. But you still want to have a relatively high level of usability. So you want a high performance at a low power. You want the best of both worlds. And so they're really optimizing for performance per watt. And actually, it helps at the other end too. So if you optimize this for performance per watt, you can scale it up to a bigger, faster chip that's going to be faster than it would have been otherwise, because you're constrained by the number of watts you can feed the thing. And sort of the third tier of GPUs is general purpose computing. I've included a long list of things here. On the research side, right now, 3 of the top 5 on the top 500 list are running NVIDIA GPUs. Lots of simulation codes have been ported to GPUs. There's a huge, huge industry in computer science and computer engineering fields where people are developing GPU algorithms and publishing papers on how to do computations fast on GPUs. Just a few applications where they're being used: astronomy, materials, CFD, weather simulations, and on and on and on. And while what gets the limelight is when you talk about running simulations on GPUs, I'll also add that if you get a big data set that you need to analyze, it's not as sexy as running a simulation, but you can write a very simple GPU algorithm to perform your data analysis instead of doing it on the CPU, and you can get a performance benefit just for doing those types of mundane tasks as well. On the consumer side, they're used to accelerate image processing, 3D rendering, like drawing a blank on the word here, like 3D Studio Max type stuff, where you're doing architectural renderings, or you're doing rendered movie, the Pixar type animations. They're doing that kind of stuff on GPUs now. You can use them to compress videos faster, and the list goes on and on. And I'll insert a advertisement here from my own code. If any of you are interested in molecular dynamics at all, HumDBlue is a general purpose MD code written entirely on GPUs. I work in the Glotzer group at the university here, and we're using HumD to simulate varied systems of tethered nanoparticles and other polymer systems, hard particle self-assembly, It's a very, very general code. All these are being simulated in HMD on GPUs right now. So let's take a step back for the moment. That's kind of where things are, but let's look at how we got there so you can understand where these GPUs came from and why they're built the way they are. So I can call this GPU prehistory because I have lived for this entire time, if only barely. And computers back then looked a lot different, but they're really basically still the same things today. You have a central processing unit, and it's connected to a certain amount of main memory. And there are other connections that you can insert cards into. And this is where video cards got started. So video cards originally looked like this. They had their own independent device memory. I'm introducing terms here that'll be used later. So I'm calling this device memory. So it's RAM that's separate from the main memory that the CPU is connected to. And then there's a little chip that basically takes an array of device memory and draws it on the screen. And the way that you could draw any arbitrary graphic on the screen was to write pixels into the device memory. And then those pixels would show up on the screen. So, and games were developed on this. And so the performance and the detail that they could put into the games was limited by how fast the CPUs could compute the pixels to write into the device memory. So it didn't take very long. We got to 1997 when 3DFX introduced the Voodoo 1, which was the first real GPU. And so they took the idea of this video card and transformed it into a video accelerator. So they actually added a processing chip onto the card. So now the card has its own memory still, but it also has its own chip. So instead of the CPU computing all the pixels and sending it the data to render, you just send it the triangles that you want it to draw, and it takes care of doing all the calculations to draw the triangles, for example. And since then, it's only exploded, and we'll talk about that in a moment. But this chip, it's more than just a second chip. It's not just another CPU. It's not the same architecture. It's a very, very different beast of an architecture. And so now I'm going to fast forward to today's architecture, specifically the NVIDIA Fermi architecture, and compare that with a CPU architecture. I get this question all the time. Well, it's transistors on a chip. Why is it so much faster than a CPU? How could it possibly be? And this slide attempts to answer that question. So a CPU looks like this from a high level. There's a large amount of cache and a very small amount of compute. This is in terms of the total area of transistors devoted to the chip. And you have a really fairly low latency connection to your DRAM, and I'm going to call it low bandwidth, and this is low bandwidth only in relative terms. The GPU looks very different. You'll see a lot more blue here, a lot more transistors devoted to performing compute operations, floating point, add, multiply, divide. That's what I mean by compute. And the cache is sort of spread around the chip a little bit more, and there's a lot less cache, relatively speaking. A CPU today might have 6 megabytes of cache. A GPU, I don't remember the exact number off the top of my head, but it's somewhere around 1 megabyte or so. It's a lot less cache. And it has a connection to its own device memory, or global memory is the same term. And that connection is very, very high bandwidth. These things are 512 bits wide and operating at high clock speeds. But as a consequence of this pushing this bandwidth so high is that there's a high latency as well. But I put a star here because it's not, the latency really doesn't matter. And I'll get to that on the next slide. What else? Yeah. Okay. So, okay. Or actually the slide after. So how do they build these GPUs? There's one fundamental unit of construction. It's called the multiprocessor. And specifically for the Fermi architecture, each multiprocessor has 32 CUDA cores on it. A CUDA core, if you know anything about CPU architecture, you might call it an ALU. Each core is capable of performing a 1 floating point multiply add per clock tick. And so with 32 on a core, or with 32 cores on one multiprocessor, each multiprocessor can perform 32 multiply adds each clock tick. Going along with this is a scheduler, a small amount of cache, and registers. So the total cache per multiprocessor is 64K, 32,000 registers, and these things, if you still are aware of the myth that GPUs aren't floating point IEEE compatible, then, well, the current generations are fully IEEE floating point. You know, there's no sacrifice to accuracy. And, well, I'll get to that number in a moment, but you take this multiprocessor, and to get a GPU out of it, you copy and paste it, and you put 16 of them all on one die and tie them together with cache and memory controllers and everything. So it's a scalable design. They tend to design the highest end one first, and then to make less expensive designs to target the lower cost markets, they build chips that only have 8 multiprocessors on them, or your laptop GPUs might only have 2 multiprocessors on them. And this scalable design is key, and it will show up in the programming model as well. So, but the last number that actually means a lot for the programming model is that just one multiprocessor is capable of processing 1,536 active threads at once. Compare that to your quad-core CPU can run 4 threads at once. The entire CPU can run 4 threads at once. Just one multiprocessor here can do 1,500 threads at once. And that's how we get around this high latency problem. So instructions are processed in warps. So I mentioned this on the last slide. There's these 32 CUDA cores, but there's only one instruction scheduler. So all 32 cores are performing the same instruction at the same time, just on different data. And that group of 32 is called a warp. So that's the most fundamental unit of execution. But out of all these warps that are running on the device, they can all be doing different things. You can have one warp goes out and says, I need some memory from DRAM. And the memory controller says, OK, I'll go get it for you. Why don't you wait while I go get it for you? So that warp actually goes to sleep. Well, the clock keeps ticking, right? So there are more useful things the hardware can be doing. If there are other warps running at the time, they could use that clock tick to do a multiply or an add. Maybe another warp comes in, it makes a memory load request, so it goes to sleep. This warp comes back online and does a subtract. Okay, and now the memory load that was issued up here now arrives. And so that first warp can wake up and actually perform the operation that required the memory. And so this interleaving between different threads or different warps is happening per clock tick. And this can be done because we have 32,000 registers on the multiprocessor. There's no context switching overhead. Everything is all resident in registers, and these things can swap between per clock tick. So it's called latency hiding. While some of your threads are waiting on latency, other threads are doing useful work. And there's a trade-off here, which we'll see when we get to the example much later in the talk. So a couple terms, if you're not aware of these concepts. Peak memory bandwidth is just a number you assign to the device, and it simply comes from the number of bits wide your memory bus is times the data rate times the clock speed. So it's the peak possible number of bytes that you could possibly transfer from DRAM to the chip and back again. Peak gigaflops is a similar calculation. It's just the number of processor elements times the number of operations performed per clock, which is 2 in the case of these GPUs. They can do, actually I was being lax earlier when I said multiply add. It's actually an FMA, fused multiply add. So it counts as 2 instructions, or 2 floating point operations, sorry. And then you multiply by the clock speed to get the total number of flops. What do these numbers look like? I've made this plot for GPUs going back to 2003, all the way up to the current GPUs. And I put a little question mark here because we're on the verge of the next generation chip coming out. It's anticipated, it's called Kepler, the code name is Kepler, and it's anticipated any time now, although I don't think it'll be available for sale until spring, but that's just my guess. But look at these numbers. So we start, right now, we're at over 1,500 gigaflops, or 1.5 teraflops single precision compute capability on one chip, one GPU. And I'm plotting CPU here too, but I stopped tracking it because it's so hard to figure out what their peak is anymore, and it's so slow that it just doesn't compare. Same thing for memory bandwidth. Right now, we're at just shy of 200 gigabytes a second of memory bandwidth between the GPU and the DRAM. Compare that to CPU memory bandwidth is somewhere around 25 or so. I don't know what it's gone up to today, but it's not going up that fast. Right. So today, there are actually 3 major competitors in the GPU market. NVIDIA, AMD, they've actually dropped the ATI brand name now. I should update my slide, but I haven't. And Intel. Intel primarily makes integrated GPUs for laptops, and although by some measures they are the biggest, they have the biggest market share, they only have the biggest market share if you count all the laptops that are sold with Intel cards. They're not really of interest for high performance computing today. So, and NVIDIA and AMD are extremely competitive in the high performance video game arena. NVIDIA will release one and they'll have the fastest card, but only for that month, and then AMD will release one and they'll have the fastest card, and then NVIDIA will have the fastest cards, and they're constantly fighting for the top. But I'm only going to talk about NVIDIA for the rest of this talk, partially because it's what I'm familiar with, but also partially because while they're competitive on the hardware side for gaming, AMD's software is not that great for programming GPUs, and I don't think it's worth spending time trying to program for them. So, but that's my opinion. Some numbers, just in the second quarter of 2011, 140 million, and right now I'm talking about desktop GPUs, not the smartphones and stuff. 140 million sold in second quarter, and because of all this competition, there's enlarged demand. They're very inexpensive and very, very widely supported. So, I was going through this with my wife last night, and she mentioned I really need to say that, that I'm only ever talking about the top of the line, fastest GPUs in these talks because I care about fast benchmarks and things like that. But GPUs range from $50, and all of these are can be done. You can do general purpose computing on any of them, all the way from the $50 GPU that's might be in your desktop, just a standard Dell desktop that the university buys thousands of, to the $500 super fast GTX 580, which you would have to spec out a custom machine to get, or add it to your machine if you have a power supply. So, and even laptop GPUs, as I said earlier, you can cut out multiprocessors to get down to a really low power GPU, but your laptop may have an NVIDIA GPU in it that you could program with CUDA. Or Macs recently have gone to AMD GPUs primarily, and if you want to program that, the OpenCL is an option. I'm not going to really talk about OpenCL today, but you can read up on it. The concepts are identical. It's just a matter of the execution. The actual lines of code you have to type are different for OpenCL than they are for CUDA, but at a high level, everything is identical. So with that being said, I'm talking about the high performance stuff here. GTX 580 is the current fastest single silicon GPU you can buy. Costs around $500. It has 512 processor elements. These are the CUDA cores I mentioned earlier. Around 1.6 teraflops. I mentioned the memory bandwidth. And now, but server room guys will say no if you ask them to install 1,000 of these types of computers in the server room. It can't be done. So if you go to a server room friendly architecture that is capable of running at high heat and for 365 days a year, there's this Tesla series, which if you actually look at the numbers, it's slower, except for double precision. It's faster. But you pretty much have to buy this if you want to buy a few hundred GPUs and put on a cluster. And when you actually look at the costs, it actually works out better in the end to buy these systems. So I could show a lot of very detailed benchmarks, but you get lost in the details, I think. And so these are numbers from my code running what I would call a typical benchmark. And a speed up, I measure speed up in terms of what would I have to run in an MPI parallel program to get the same performance. So when I say a speed up of 80, I mean that I can run on one GPU, or I can run an MPI optimized program on 80 CPU cores on an InfiniBand system. So that's what I mean by 80. And if you compute out the put in some somewhat arbitrary costs, you can figure out that the amount of speed up you get for the dollar you put in is 16 here. Whereas on this end, the computing costs are higher for the GPUs, but they're also higher for the CPUs. And even though your typical speed up is slower, your speed up per dollar is actually more. So you'll get more for your dollar that way. I don't know. It's all speed ups are so very arbitrary. If any of you have a different definition of speed up you'd like to talk about, I'm happy to discuss it. And another reminder, feel free to interrupt me. I don't mind being interrupted at all. I'm going over a lot of stuff. Okay, so we've talked about the hardware, sort of how we got to where we are and what the current architecture is. Hopefully I've convinced you that the GPU architecture is very different from a CPU architecture. You aren't going to be able just to take GCC or the Intel compiler and compile an existing application to run on the GPU. The architectures are too different. It's not going to work that way. So there have been specialized programming environments that are designed specifically for programming GPUs. Now, I was digging through slides to build this talk, and this is actually a 4-year-old slide when CUDA was new. That's another thing I should say more than once today, is that CUDA is actually 5 years old now. So GPU programming is very well established. It's been around a long time. It's very mature. But when it was new, there were all the other stream programming options that were available. And if you're interested in the GPU programming history, I urge you, go Google some of these things and look them up. But for the purposes of today, if you want to write a new application, don't even think about them. There are 2 ways to program GPUs today effectively. If you're doing graphics, you'll definitely want to use either DirectX or OpenGL. But if you're doing general purpose computing, which is the point of this talk, you'll want to use either CUDA or OpenCL. CUDA is NVIDIA specific. If you write something in CUDA, it will only run on NVIDIA cards. OpenCL promises vendor independence, but excuse me, it's a little harder to program than CUDA. Specifically, I've never even touched OpenCL because a lot of things I do are in C++, and OpenCL is somewhat backwards in that it only supports C, not C++. And if you think that OpenCL might be a panacea and that you just write one code and run it on all these different platforms, the people I've talked to that have programmed OpenCL say that's wrong. The platforms are still different enough. Say the differences between the NVIDIA cards and the AMD cards are different enough such that you still program one code specific to NVIDIA and one code specific to AMD in order to get the peak performance out of it. Right. So if Fortran is your forte, there is Fortran CUDA support. It's made by a third party, which I'll mention later. It's PGI. What are my other comments on this? I find CUDA very easy to learn. In fact, I'm aware of MPI. I'm aware of the concepts and some of the implementation details, but I've never actually written an MPI program myself. But I've written lots of CUDA applications, and I find CUDA is very, very easy to write, I think. And it's C++, so it's a high-level language, but it is close enough to the hardware that you can very easily get near peak performance. When I talked about the peak memory bandwidth and the peak floating point operations, you can get those numbers, and my example later will show that. Right. So now on to some resources. So specifically, this is a very introductory level talk. So these are resources if you want to learn more, or if you want to use GPU computing here at the university. I'll start with CUDA. So CUDA itself, as I've said, it's 5 years old. It's very mature, very well-developed product. It comes with a lot of tools. There's a compiler. So this is a C++ compiler, as I said. And what it has is there's just a few special directives that are added on top of C++. And these special directives are to make it so you can program for this device that's capable of running 30,000 threads in parallel. And I'll show you examples of what those directives are later in the talk. There is a debugger, CUDA GDB on Linux, and there's NSIGHT on Windows. NSIGHT has a GUI, CUDA GDB does not. I'll get to Linux GUIs in a moment. But in either case, it's a full hardware debugger. You can set a breakpoint in the code, step into it, inspect variables. Everything you expect from a debugger you can do. It's a little weird debugging when there's 30,000 threads in parallel. How do you choose which thread you want to break in, and how do you switch between threads, and maybe those threads happen to be running on the device at the same time. So there's some caveats, but it is a fully capable debugger. And then there's a profiler, and I'm listing 3 names here merely because NVIDIA keeps changing the name of the profiler. So depending upon which version of the toolkit you download, you might get it by any of these 3 names. It's continually being improved, though. This is the latest version in the CUDA 4.1, which I don't think is out to the public yet, but will be soon. I haven't even had a chance to play with it yet, but it looks like they rewrote the thing from scratch. So it's a pretty, at least the previous version was pretty sophisticated. There's all sorts of performance counters. It counts cache hits, cache misses, memory accesses, number of instructions executed. The list is this long. And then so there's this deluge of data, but the newer versions of the profiler actually perform analysis on that. And so it'll take all those counters and it'll generate for you how much memory bandwidth is your code using, how many instructions per clock are you getting, and high level quantities like that. And so you can use that to profile your code and understand where the performance bottlenecks are. And then lastly, to aid in debugging, there's a program called CUDA memcheck. And I don't know how many of you are familiar with Valgrind, but it's basically a tool that will tell you if your code is writing to out-of-bounds memory or reading from out-of-bounds memory. Invaluable tool for debugging. If you've never used it before, highly recommend, even if you're just doing CPU code, Google Valgrind and check it out. CUDA also comes with lots of libraries. So NVIDIA is really committed to supporting general purpose computing on GPUs and science in particular. And so they have actually funded and develop and provide a lot of libraries that come with CUDA itself. So if you need BLAS types operations, you don't have to program it yourself. They're already there. There's a library. FFTs are already there. Sparse matrix operations, there's a library for that. Thrust is really cool. It's a C++ template library. And now you might imagine, won't get into the details, but on this, if you're running 30,000 threads in parallel, how can you do something such as simple as sorting an array? It's actually a very challenging problem to sort an array of numbers with that many threads in parallel. But the computer scientists have solved the problem, and it's implemented in this library. So you just have to call the library if you want to sort. Parallel random number generation. If you have 30,000 threads running in parallel and each of them needs their own stream of random numbers, how do you guarantee that you have 30, or not even just 30,000, if you have 1 million streams, independent streams of random numbers, how do you know that they're going to all be independent? It's a really challenging problem. People have figured it out, and NVIDIA has published this CURAND library that does it for you. And if you're into image processing, definitely check out NPP. It's called NVIDIA Performance Primitives. That I'd never used it myself, but just looking at the documentation, there's tons of image processing functions built into it. And then this is just NVIDIA-provided libraries. The number of third-party and other open-source libraries, there's so many of them. You can Google them, or NVIDIA has actually compiled a list of the really high-profile ones on their website. So there are additional programmers tools. If you use DDT or TotalView, both of these debugger products have a CUDA module now, so that it interfaces with CUDA GDB, so you can debug CUDA programs on Linux. Tau and Vampire Trace interface with the performance counters, and PGI is providing various levels of compiler tools. So CUDA Fortran basically lets you write CUDA code in Fortran. CUDA for x86 is cool. I really want to try it out, but I haven't found the time yet. It actually takes your CUDA kernel that you've written for GPU, but instead compiles it for a multi-core CPU. So you don't have to, if it works well, the idea is that then you wouldn't have to write a multi-core CPU optimized code if you want to have both code paths, CPU and GPU. And then this is something, if I'm trying to cover all the bases here. The talk mostly focuses on CUDA, low-level CUDA programming, C++ CUDA programming. But if that's not your forte, if you want to do something higher level, one thing you might check out is there's this, the PGI compiler has something called accelerator directives. If you're familiar with OpenMP, these are OpenMP-esque directives that you insert into your code, and then the compiler will automatically generate the kernels for you and run them on the GPU for you and handle copying data back and forth. So it's a high-level way to get speed up from the GPU. I've never done it myself, so I can't answer specific questions, but I've seen presentations on it, and I'm aware of it. All right, so but if you do want to learn the nuts and bolts of low-level CUDA C++ programming, I've compiled a list of educational resources here, and I do believe these slides will be available online at the CI Days website, so you can get all these links afterwards. The CUDA programming guide, I highly recommend. It is a manual, but I do highly recommend reading it cover to cover. It really lays out, it's really well written. It lays out the hardware model, like I did at the beginning of this talk. It lays out the programming model and then all the different things you can do with it and how to get fast performance. And then there's something called the best practices guide, which also gives you specific recommendations on out of all the different things you can choose to optimize, which ones should you optimize first and which ones should you optimize later. The CUDA SDK is a really great set of examples. It's code provided by NVIDIA. And these things, they actually have, there's a sort example and a reduction example, and they also have like a computational fluid dynamics example. So they range in complexity, but pretty much all the examples that come in it also come with a PDF that describes the details of the algorithm, why it's set up the way it is, how they optimize it to run on the GPU, and so forth. If I were to pick one of all the myriad of online recorded courses, I would point you to this one. There's a course by Wenmei Hu at the University of Illinois Urbana-Champaign. They have videos and slides. You can go there. He's been teaching it. He was actually teaching this course before CUDA was released to the public. They had NVIDIA come and give special access to all the students of the course. I'll say a little bit more about this in the next slide, but there's a summer school sponsored by the Virtual School of Computational Science and Engineering. And if you go to this website, you can find recorded lectures. So this is taught by Wenmei as well. So it's a shortened version of this course. And more. So NVIDIA has another great web page listing all the different CUDA textbooks and other courses like this, and so on and so forth. But we're here at this is CI Days at the University of Michigan, so I have to tell you what is available here today, and the answer is at Flux. So if you buy time on Flux, there are, out of all the nodes on Flux, there are 8 Tesla GPUs available. Right now, there's nothing special about them. You just get your normal allocation. You don't pay any extra, and you can request that your job run on one of these GPUs. And I urge you to talk to the CAC or Flux support or CAC support about how best to schedule these, because there's some tricks. And if demand for these increases, so if all of you go out and start programming CUDA tomorrow and all of a sudden there's hundreds of job requests every day for those GPUs, they will build out and add additional ones, but there are currently no concrete plans to do that. And if they do build it out, they may charge extra for GPU core months versus CPU core months. On NICS, if you're in the engineering college, there are 4 previous generation GPUs in the general queue. And then specifically within our group, we have 128 plus of the current generation and 48 of, my number's wrong, 48 of the previous generation that are privately owned by us. So we're the biggest GPU users on campus right now. And then it goes down. I mean, I know the Kane Labs, a lot of the Kane Lab computers actually have NVIDIA Quadro GPUs in them, which are, you can run CUDA code on, and you know, maybe even your desktop and laptop, like I was saying earlier. You can, these things are everywhere. And then lastly, this many-core summer school shows up again because it's, not only is it organized out of the University of Michigan, we also are always a site here. And so this is a summer school that's taught, the last 2 years we've had 10 sites linked via high definition video feeds. And so it's being taught from Illinois, but you have everyone sitting in front of a display here in Michigan and interacting. You can interrupt the speaker in the middle of his presentation and ask a question. And it's just like being in the room with them. And it's a real great, I'm involved in organizing this, so if you want to learn it, we run it approximately every August, so definitely check it out. And then lastly, if you're interested in even higher level tools for using GPUs, they're there. MATLAB, LabVIEW, and Mathematica all have support built in for them now. And if you use certain graphics tools, Photoshop, AutoCAD, 3D Studio Max, things like that, they have GPU accelerations built in. I don't really know a lot about these because I don't use them, but they're there if you want to go look up and check with the vendors for more information. So that kind of ends my whole overview of what GPUs are and where to get access to them and where to learn more. So now I'm going to drill a little bit more into the details and actually show you a hello world program on a GPU. So please feel free to interrupt me with any questions as I go along here. So I introduced earlier that these devices are massively parallel is a term that's used for them. You're running, they're actually actively running 30,000 threads at once. And you can throw a problem at them of any size. You can throw a problem at them and request that 10 billion threads be run. And while today's GPUs will only run 30,000 at a time, tomorrow's GPU might run 100,000 threads at a time, or 1 million threads at a time if you think 10 years down the road. And so just the same problem, the same CUDA kernel, just running on newer hardware will exploit more parallelism. And so this is extremely fine-grained parallelism. And it's exposed to the programming model that way. So here's my brief example of something really simple that you might do. You might have an array of elements in memory, and you want to double every element. On the CPU, you would write a for loop, and for each iteration of the for loop, you would say that AI is 2 times BI. okay? And the CPU is going to go through and one at a time multiply elements by 2 and do the memory movement and everything. The data parallel approach is, it's almost like you just take this outer loop and remove it. One way to think about it. So you write AI equals 2 times BI. You write exactly the same code. If it's C code, you literally copy and paste the inside of the loop. But then instead of having this for loop on the outside, you just tell the device, I want you to run n threads in parallel. The device says, okay, I'll run n threads in parallel to the best of my ability. And it goes, and if it has enough parallel functional units, it will do all those multiplications and all those memory units all at the same time. So, yeah. Some terminology that you will run into using CUDA and that I will use a little bit later in this talk is, this is a device memory array. So it's an array of memory, array of values that's sitting inside a device memory. So the device memory is the memory that's on the graphics card board directly connected to the GPU. And arrows on my slides mean that I'm moving memory from device memory, for example, in this case, into a thread register. So thread registers are local to the multiprocessor and can be accessed in a single clock tick. So they're extremely fast accesses. There's no latency to accessing values in a register. Threads are grouped into warps. I talked about this a little bit at the beginning, where the warp size is 32. On my slides, the warp size will be 5 blocks because 32 would be too busy. And then you actually combine these warps together into blocks. And the block, at a high level, is just a way of saying, these threads belong to this block. But functionally, what it allows is that there's some synchronization capability. So there's actually a barrier synchronization in there. If you're doing calculations within a block and you compute one value and then you need the value of that one value across all the threads of the block before you continue, then you can put a barrier synchronization. But you can only synchronize across within one block. And then there's also something called shared memory, which is somewhat of a more advanced topic that I'm not going to discuss anymore today, but threads within a block can access a pool of shared memory. And blocks on the current generation hardware can be up to 1,024 threads. And then similarly, a device memory array you can write into it. Okay, so now memory access patterns. So the GPU cache is something it's a little bit hard to wrap your head around at first. On the CPU, the cache is fairly simple as long as you don't dig too deep. The things are, if you access one element, the CPU cache is going to prefetch the next n elements. And so you normally want to write your code such that if you're looping, you loop through elements in order and you don't jump too far ahead, okay? But that's the worst possible thing you can do on a GPU. The GPU there's this two-dimensional execution model. So not only do you have the threads looping, so if I were to have this thread looping, it would access one element here and then another element later and another element later in time. But you also have all these threads running in parallel, accessing elements at the same time. And so the way that the cache works on the GPU is when this thread goes out and requests a value from memory, the GPU is going to bring in the whole cache line. And that cache line is delivered to the multiprocessor. So the expectation is that you have a memory access pattern like this. All these threads in a row are accessing memory elements in a row, so that that entire cache line is consumed. If you have a memory access pattern like this, which for the sake of my example here, let's assume that each one of these accesses is hitting a different cache line, then the memory architecture is going to bring in a whole 128-bit cache line, and just for this thread, and then he's only going to read one value out of it. And then the memory architecture says, oh, this thread needs another cache line. I go bring in a whole 128-byte cache line, but I only use 4 bytes out of it. You're you're not going to hit the memory bandwidth capabilities of the device that way. So while the current cache is pretty it's pretty good at handling these types of accesses. So on the earliest GPUs, you absolutely had to rigidly follow this pattern, and actually there were a lot more restrictions on it, and it was a performance cliff. If you even deviated in one little way, then the GPU would immediately reward you with like a 1/32 performance reduction. Your performance would go down by a factor of 32 immediately. The new caches are a lot better. So as you slowly go from completely coalesced like this to completely uncoalesced, the performance is a slow drop off, not a cliff. And there is, if you're familiar with cache levels at all, there is a 768K level 2 cache that's shared across all the chips, all the streaming multiprocessors. Okay. Yes. Okay.
On your array example there, where you were parallelizing the loop, I'm having trouble. I'm sure this is probably just because this is kind of a simplification, but I'm having trouble picturing where you're defining your array subscript when you parallelize this. Are you assigning that to each thread?
Okay, so the question is, how am I assigning array subscripts to threads? And for this simple example, I'm using the simple assignment of the array subscript is exactly equal to the thread index. And this is a very common pattern in CUDA programming. It doesn't have to be the assignment.
You can have a way to address each thread by index.
Yes, and I will show an explicit example of that in a few slides. So, yes. So, but in terms of assigning values to threads, so I'm showing this example here where I have one array element per thread. That's a choice. You could assign 4 array elements per thread, or you could assign, depending upon what you're computing, if the amount of computation per array element is actually fairly heavy, you could assign 32 threads per array element. The limits, there's nothing imposed on you by the programming model that requires you to do one thing or another. The only thing you have to keep in mind when you do this assignment is this memory access pattern. And the best practices guide will tell you, and I'll repeat, that you think about this access pattern first when you're doing your layout of threads to array elements. And then after that, think about the other impacts.
Well, what if you don't really have a direct correlation between thread index and your array?
So if we have time, I will get to a specific example in my code where there's a semi-random access pattern, and I will talk about how I dealt with that. Okay. I'm a physicist by training, so hello world for me, that's more than just vector multiplication, is a mass spring system. And so for this very contrived example, I'm going to simulate 1 million mass spring systems independently. All right, there's a lot of good things that come out of this. The point of this is to show you some basic CUDA code, to show you how simple the CUDA code is, and also to have a tweakable parameter that'll produce an interesting graph a little later. So hopefully you're familiar with Euler integration. This is just a very simple application of Euler's method to compute the position of this mass on a spring over time. Okay, so here's the actual code that does it. Hopefully it's big enough to read. If not, these slides will be available online afterwards. So let me point out that this is code that runs on the GPU. So this is C code, C++ code. And we start, as you normally do in C++, by defining a function. And so this function is defined, it looks like a normal function definition. There's the name, the arguments, and everything. The only thing that's different is there's this little __global thing out front. And this is a flag to the NVCC compiler to say, hey, NVCC, this is a GPU kernel. I want you to compile this code for the GPU, not for the CPU. So that's all that that's about. So to compute the thread index, remember that there are blocks, and you assign n threads per block. And what I'm going to do here is the same thing as that simple array example where I have one thread per array element. And so to get a global index from 0 to n, I need to take my block index, multiply by the width of the block, and then add the local thread index. Okay? These indices can be 2 or 3-dimensional as well. So a lot of times if you're doing matrix processing, if you want to assign one element per thread, then you would actually use blockdim.y and threadidx.y as well. But this is the most common indexing pattern for 1D arrays. And because the number of springs might not be an integral multiple of the block size, say my block size is 256, but I have 257 springs, we do have to do a bounds check and go quit threads that would access past the end of the array. If you forget this line, CUDA memcheck will nicely point out to you that you're accessing past the end of the array when you get to this line. Okay, so my spring is stored in a struct, and I'm accessing array elements just the same way you would access an array element in C++. I have an array, I access the index, and assign it to a local variable. Now I always write the code this way because I like to explicitly see, okay, this is global memory or device memory, and I put little d underscores in front of device memory pointers so that I can see, okay, that's a device memory pointer. And then the compiler will extremely, extremely, extremely aggressively place all local variables in registers. The only time it will not do that is if you index a local variable with a random index, or not compile time determinable index, or if you end up needing more than 64 registers per thread on the current hardware, then it'll spill to memory. But those are rare cases, so I look at this as saying I have a local register is a load from global memory. Okay, we'll pre-compute just a couple constants that'll go outside the loop, and the NVCC has a few pragmas you can use to direct it. In this particular case, it's not very smart about unrolling the loop, so I tell it to unroll the loop 16 times. And then here's my loop, and so I said this is a very contrived example, and it is. And what I'm doing is in this loop, I have n steps. So I read in the spring from memory, and then I perform n time steps on that spring. Okay, so this is just the application of the Euler integration. And then I write the final value out to memory. And so this n steps is now a parameter that I can tune, and it's going to make a cool graph in a couple slides. Okay, so that was, oh shoot, now I'm gonna have to go through that all again. Actually, let me, this is all the GPU code. So now I'm going to go to the CPU code that's necessary to go along with that. If it's not immediately obvious, a GPU does nothing without a CPU. The GPU is it's a coprocessor on a card that's plugged onto a main board. It takes instructions from the CPU. And so your code mirrors that. You write one code that has some code that runs on the GPU and some code that runs on the CPU. So this is inside the main function that runs on the CPU. And what do? Well, beside some constants, we allocate memory. So this is just using the new operator in C++ to allocate memory for the springs. Now remember that the GPU has its own device memory, and it's separate from the host memory that's attached to the CPU. 2 separate memory spaces. So there's a second type of call called, it's a CUDA API called CUDA-malloc that allocates a block of memory on the device. So new allocates memory on the host, CUDA allocates memory on the device. There'll be two different pointers, but the CPU can't directly write into the GPU memory by pointer. If you want to know more about it, that there's ways around it and things you can do, but this is the simple model and the way that you most commonly use it. So all I'm doing here is I'm just looping over, and to exemplify what I said, I need to write my initial values, which in this case are random numbers. I need to write all those initial values into the host memory, which to keep myself from getting confused, I label h_springs for host memory. Okay, and then there's an API call called CUDA memcopy that copies memory from the device to the host, or from one area on the device to another area on the device. Now, I'll point out one thing. This is an old example. If you program this with CUDA 4, if you go and look in the CUDA 4.0 manual, this last argument won't be there. You used to have to always tell the call, I want a copy from the host to the device or from the device to the host. And if you get it wrong, you get an error message. But the new version of CUDA is actually able to figure it out for you. And the reason is that they put the pointers in separate address spaces. So they can tell just by the value of the pointer what direction it's going. Yes?
So can you write the main routine for the GPU? Just both main routine and everything for the GPU. I mean, here.
Oh, okay. So okay, I understand. So the question is, can you write the main routine to run on the GPU? And the answer is no. The GPU is always taking instructions from the CPU. So there always has to be some amount of code on the CPU that sets up the call to the GPU and then makes the call. It can be very small. If your code on the GPU can run by itself for a long time, then you can have a very small amount of setup and then a big call on the GPU. But you have to have a main function still on the CPU. Okay, and in good programming practice, you always check for errors after API calls because you will get very annoyed at debugging things if you don't. Okay, so and then the last part of the main function is to actually make the call. So the first step is we need to tell it how many threads to run. And remember that the threads are split into blocks. So you choose a block size, and then the grid size is the number of blocks. So I'm being very lazy here, and I'm just taking the number of springs and dividing by the block size, but the division might round down, so I just add 1. You can be more picky about that if you want, but this is the lazy way of doing it. And then to call the kernel that runs on the GPU, you make what looks just like a normal function call. So update springs GPU, and then there are the arguments I'm passing the function call. There's just this extra little thing in the middle, this triple angle bracket thing that you specify the grid size and the block size to tell that function call how many threads to launch. So the kernel, right? I only wrote one kernel. That there was just one piece of code, and this is telling it how many copies of that code to be executing in parallel all at once. So it's a little, I see confused faces. It's a little weird to wrap your head around right at first, but it's actually a very easy way to program parallel computing, I think. I find it very natural and very easy. This particular example code I wrote in a matter of 10 minutes. Okay, so the question is this part of C++? And the answer is no. This is the extension that NVCC adds on top of C++. Okay. Right. So what happens when I run this code? And it's a contrived example in more than one, and more of the way than one. So we'll see that in a moment. So here is I compile it, which I forgot to make a slide on this, but I'll just mention it, and if it sticks in your head, it's a good thing. I like CMake for generating make files. CMake has internal support built in for handling CUDA files, and so it's trivial to compile CUDA files into an executable, and it will automatically call NVCC the way it needs to be called in order to compile things. So if people are really interested about that, see me after, and I can show you the CMake code for this example, which I forgot to build a slide on. Anyways, so if I run it on the GPU, and in this case, the GPU is that GTX 580 I was talking about at the beginning. At the parameters I have on the slides, it runs in about 5 milliseconds. And if you compute the effective flop rate that you're getting and the effective memory bandwidth rate that you're getting, it's 1,120 gigaflops and about 5.5 gigabytes a second. So if you're not aware of this, that there's the two limits, you can never, unless you have the perfect combination of instructions, you'll never hit both limits at once. You're always going to run into one limit before the other. So if your code is floating point heavy, which it is in this case, because I set the number of iterations to 1,000 or something, it copies the data in, performs 1,000 iterations, and then writes the result back out. If you're floating point heavy, you'll hit that limit first. But if we only run one iteration and then write the results back out, we're going to be performing a lot more memory operations. And so we'll actually hit the memory limit first, which I'll show you on the next slide. But for a counterexample, if I take the same code and I sprinkle some OpenMP around it and put it on the CPU, it runs on NIC's login, which is Xeon E5540. It runs at about 8.5 gigaflops. Now, could you do better on the CPU? Well, probably. But my point for this slide is that I put the same amount of effort into the GPU version as I did into the CPU version. And the speed up comes out to about 130 in this case. But the really cool number is the fact that this 1,120 gigaflops is 70% of the peak. Most applications, you're not going to hit 70% of this peak flop rating. You're going to hit 70% of the peak memory bandwidth rating. But just wanted to show that just very simple C++ code that doesn't have assembly language in it or anything is able to hit that close to the peak capability of the device. And like I said, I spent 10 minutes programming this. So here's the cool plot that I've mentioned several times now. So here I'm varying the number of steps in that inner loop. Now, ignore the little spikies. They are just an effect of the loop unrolling, which is too hard to explain right now. But just look at the trend and how the memory bandwidth here, and I'm plotting this as a fraction of peak performance. So when I'm only performing one iteration between reading the spring in, perform one iteration, write the spring out, that's a lot of memory operations with only, say, of the order of 10 floating point operations in between. I'm hitting 85% of the peak memory bandwidth capabilities of the device without even really trying. I can get that close to the peak. And then as you increase the number of steps, the memory bandwidth is staying identical, which says something interesting about the time, which we'll see on the next slide. But it's only when you get up to of the order of hundreds of floating point operations per memory read that the memory bandwidth starts coming down and our floating point operations start going up into that peak. So, yes. That's,
about 10 minutes left.
so, and then after that, questions? Okay, so I will hurry through the rest of this then. So what does that say here is that if I actually look at the time of execution, I can increase the number of iterations from 1 to 10, doing 10 times more work, but it's executing in the same amount of time. So this is because it's waiting on the memory. So if you come away from this with anything, just come away with the concept that on GPUs, floating point operations are free. If you can save one memory operation, and in place of that one memory operation, you can do 20 floating point operations, or even 50 floating point operations, don't worry about the extra floating point operations. Save the memory operation. That's worth a lot more. And it's only, it's called the memory wall, and it's only going to get worse over time. So it's not obvious from the plot I had at the beginning, but computation is going up exponentially. Memory bandwidth is going up linearly in time. So algorithms over time should evolve to be more computation heavy at the expense of doing less memory operations. Anyway, so I have a few minutes, so let me just briefly talk about molecular dynamics, since this is the stuff that I do. I want to show you a little bit more advanced application. If you're not aware of how MD works, we have particle positions and velocities, we compute accelerations, and we time step them forward with something more advanced than Euler integration, of course. And the systems that I'm interested in simulating are coarse-grained systems. So for example, I have just a Lennard-Jones potential, and we cut it off to a zero interaction at a specified radius. Now this is nominally applied between all pairs of particles, so it would be an n-squared computation. But no real computationalist wants to wait n-squared time for their simulations to run. So we make it order n by cutting it off, and this is a reasonable representation of how far that cutoff happens. Each particle interacts with maybe 100 other particles around it. So how do we do this on the GPU? Well, we use the same algorithms that you would use in the CPU. So if you're not familiar with particle-based methods, a lot of them are built on cell lists. So here I have a bunch of particles and a list of cells. And you plop the particles down into the cells. And in the interest of time, I'm not going to talk about how I do that on the GPU. I want to get to something more interesting. And then using that cell list now, when you look at who are the neighbors of this particle, any one particle in particular, you only need to look at the neighboring 9 cells in 2D or 27 in 3D. So how do I do this in parallel on the GPU? It's actually rather easy. I just write for each particle I in parallel. This is the kernel where I tell it to run n threads. I bring in the position of particle I compute its cell index, and then I loop over that neighboring cells. And I need to, for each neighboring cell I'm looping over, I bring in the particle from that cell, do a distance check, and then append it to the neighbor list. So what does this look like in parallel? Well, here's just one warp, but you can imagine that there's 1 million particles, so there's another 1 million threads out here to the right. And each of these threads is going out to all these neighboring values, reading them all in, and it's building a list of ones that fall within the cutoff. So it's very easily to parallelize. It's just one thread per particle. It's not following that coalesced memory pattern I was talking about earlier, because the cell list, which cell I'm accessing, depends upon where that particle is in space. So think about that, and in 2 slides I'll show you how to fix it. But now once I have this neighbor list, I can compute that Lennard-Jones pair potential between particles. Simply the same way. I run one thread per particle in parallel. That thread is responsible for computing the energy and force on just that one particle. And it pulls in the neighbors of that particle, which have already been generated, and loops through the list of neighbors. And now the list of neighbors is dependent upon where that particle is in space and where all the other particles are in space. So this memory load here is not going to be coalesced like I showed you earlier. So it's a potential performance bottleneck. So in any typical simulation situation that will be diffusive, those memory accesses will be completely random and will be as slow as you can manage to get, no matter how big your cache is. But you can fix the problem. So in database operations and in other fields, they use the concept of a space-filling curve to order their points, their spatially points, into index space. So this is a Hilbert curve. It starts here, and it's a continuous curve that ends here. And the color goes from red to white to blue continuously. And you can see by eye that, well, look, lots of red together, lots of white together, lots of blue together. So points near each other in space are also near each other within index. And at least as far as we know, the Hilbert curve is the best curve for doing that mapping. So if I have a random memory access pattern, and this random memory access pattern is not a generated pattern, it's what happens if I run my simulation for a while. The particles diffuse. But if I periodically order the particles based on this curve, then this figure is terrible on projectors. They just don't have the dynamic range to show it. There's just a bright line down the middle. And the bright line down the middle is saying that particle I interacts with particle j when I is almost equal to j. So that keeps all those memory accesses in a really tight pattern and increases the number of cache hits. So here I have what would otherwise be a random memory access pattern, and I've compressed it down so that I'm getting as many cache hits as I can out of the device and making that cache work for its money. Well, I'll just conclude because I want to leave time for questions.
That list of neighbors that you had varied depending on which particle you were talking about. Some had more neighbors that they were interacting with, some had fewer.
Yes. So the question.
Dimensional array. Do you have like a maximum number of neighbors or something?
Yes. So the question is about the structure of the neighbor list. I need to repeat it for the camera. The neighbor list is variable depending upon where a particle is in space. In fact, in some simulations, some particles might have 1 or 2 neighbors, and then the next particle would have 100 neighbors. And in order to make it, make the data structure amenable to that coalesced memory access pattern I talked about earlier, it is just a matrix in memory. And so the height is the maximum number of neighbors, and the width is the number of particles. And so the threads, you can imagine that in parallel, these threads are going down the neighbor list, but threads are stopping when they get to the end of their list. So it's, yes. So it's, it's by no means a uniform access, uniform computation pattern for the GPU, but it is, but the GPU handles it rather well. The performance of that forced computation kernel is entirely limited by the memory bandwidth and nothing else. So some brief conclusions, just to hit on the main points of this talk, are that GPUs are established 5 years for general purpose computation, and they're also a very available technology for use in research. If I were to assign a typical speed up number compared to CPU cores, depending upon your favorite way of defining speed up, I would say that number is 64. And the real exciting thing is that GPUs, because they're so massively parallel, today's GPU is 512 processing elements. Tomorrow's GPU might be 1,024. So if your program is written to run 1 million threads, it's going to run twice as fast on tomorrow's GPU. So you're able to take advantage of Moore's law without any problems. Still, at least today. And then there's a lot of libraries, applications, and tools available. And I like to say that data parallel programming is easy. So I'll just wrap up with that and take any questions.
Yeah, so how many ways do we have to guarantee the coalesced memory access? So in order to achieve the coalesced memory access,
Okay. The question is how do you achieve coalesced memory access? And the way you do that is before you even choose your algorithm, you really start to think about how you're going to map your data to your threads. And it's in the choice of that mapping from data to threads that you can make your memory accesses coalesced. So for any given problem, there may be, it could be a dozen ways you could think up to actually map your data elements to threads, but only some of them are going to take advantage of the memory access capability.
so do you have a control for the for loop?
You have complete control. So in the CUDA kernel, you compute the thread index, and then you access array elements. Thread 1 can access array elements, can access any array element. Thread 2 can access any array element. So it's all in how you compute which array elements you're accessing based on the thread index. So it's entirely up to the programmer to choose. The hardware has no limitations.
So was that the bottleneck of your approach, that you were per this generation? You could do that every step of your
So the question is the neighbor list and pair computation the bottleneck in MD? And the answer is mostly. In most simulations, the number of neighbors is large enough such that in combination, the neighbor list generation and pair force computation are the bottleneck. You can actually perform some trade-offs between the two and make make either one be more of a bottleneck than the other, but the optimal performance is kind of, they're balanced. The rest of the MD, which I didn't talk about, which is the updating the particles, using the force to move the particles forward one time step, that's trivial. That's the spring kernel I showed you at the beginning. You read in the current value, perform the time step, write out the value. That's easy to program, and it's more of a bottleneck than you might imagine. On a CPU, that part of the code might only be 1% of the runtime. On a GPU, it's closer to 5 to 10% of the runtime, simply because the cache is smaller on the GPU. So the data doesn't stay resident in the cache. So every time you go to perform you perform the neighbor list and the pair force, and then you go to update the particles are no longer in cache. So you have to load them back in and pay that memory bandwidth cost again to read them in, change them, and write them out. So in my own code is HUMD is general purpose enough that I keep the code separate. There could be an advantage if I rolled them together into the same kernel. It's called an uber kernel in the lingo. So no, there's the only limit on the number of particles is the memory, and the neighbor list is the big eater of memory. So HUMD can run typically 1 or 2 million particle systems on a GPU, which is bigger than you usually want to go for. I mean, if you're running that big, you should be running on 1,000 CPU cores on MPI, in my opinion. Anyways.
How come NVIDIA and the other one, AMD, are so competitive on the hardware side? It sounds like, at least from your opinion, that the CUDA is well beyond where AMD is. Why aren't they competitive on the software side?
So the question is that I stated earlier, NVIDIA and AMD are competitive, very competitive on the hardware side, but at least in my opinion, not so competitive on the software side. And why is that? I don't know. NVIDIA hires great software people. There's been a long history of it. If you look at the Linux drivers, the NVIDIA Linux drivers have always been great. And even before they were part of AMD, ATI Linux drivers were always terribly buggy. So it's just the way things have been, in my opinion. And the other thing it's fact and not opinion is that AMD and ATI, they're big fans of going for new technologies. So there used to be something called AMD. I don't even remember the names anymore, but there was one way of programming AMD GPUs using assembly language, and then they scrapped that and replaced it with ATI Stream technology, and then that existed for one generation of GPUs, and then they replaced it with OpenCL, and then so OpenCL is this open standard. It's supposed to be the way forward for everything, but now actually AMD they're starting to kind of OpenCL is no longer in the limelight. They're now talking about their Fusion technology, which it's not even aimed at us. It's aimed more at the commercial side of things. So they keep changing their technology. So if you're a software developer, you want your code to run for more than a year and run on more than one generation of hardware. What do you do with ATI cards?